Okay, so we're recording. So let me clear my screen a little bit so I got room to work. Like I said, I don't have my iPad set up as a monitor seeing what you see. So if at some point I start to talk about or start drawing a circuit and you don't see it, somebody's got to let me know that, you know, I've got to switch what I'm sharing. Okay. All right.
Got
So let's do this. Let's talk about base units. I need to make that bigger. And prefixes. So I guess the easiest way is if we set up a table. If we set up a table and wrote down the designators and the units. So if we think about the resistance, well, let's do it this way. If we think about resistance, the designator for resistance is the letter R, and the unit, the base unit, is the ohm, which we represent with the Greek letter omega. Okay. And for voltage, the designator is the letter V, and we also use the unit of volts, or the unit of a volt, which we abbreviate also with a V. If we talk about current, the designator is the letter I, because it's the intensity of the charge flow. And the unit is the ampere, which we abbreviate with an A. And if we think about power, oops, the unit, or the designator we use rather, is P, and the unit is the watt, which we abbreviate with a capital W. There's no way around it. You just have to memorize these. That if we're talking about current, we're talking about amperes, and we designate it as an I. If we're talking about resistance, we designate it with an R, and the unit we use is the ohm, which we abbreviate with omega. So, I mean, you just basically have to memorize that. As far as the prefixes go, prefixes are nothing more than a shorthand way of representing powers of 10. So instead of writing times 10 to the whatever, we can use a prefix. And the common ones, if we think about small values, if we work our way down, we have pico, which is P, and that equals times 10 to the negative 12th. If we have, the next one we have is nano, which is lowercase n. This is like a lowercase p, by the way. And that's times 10 to the minus 9th. We have micro, which we abbreviate with the Greek letter mu, and that's times 10 to the minus sixth. And then we have milli, which we abbreviate with lowercase m, times 10 to the minus 3. And again, there's no way around it. You just have to memorize them. Notice that they're all separated by steps of 3, so 3 to 6 to 9 to 12. So they're in steps of 3. That's the way engineering notation is. There are some other prefixes that are used with straight up scientific notation, but not usually in the world of electronics. So if you think about the world of electronics, you're going to see these prefixes. If we go to the larger prefixes and go from, so I guess we'll keep going this way. The next prefix up would be kilo, which we abbreviate as lowercase k, and that's times 10 to the plus 3. Then we have mega, which is capital M, which is times 10 to the 6. Notice you have to be really careful that you use M twice. And if you put the wrong mistake, the wrong letter, the classic example of that, when I had an office on campus, outside my office on campus, I had a bulletin board. And on the bulletin board, I put primarily comic strips that were technology related. So if I saw something that related to technology in the comic strip, I would cut it out and put it out. And then I saw, and I'm going to erase this in a minute, an advertisement for a walkie-talkie. All right, little handheld walkie-talkie, and it advertised 500 mega, well, they had it as MW, but whoever wrote the copy didn't realize that there's a difference between lowercase m and capital M, or perhaps whatever they were typing in didn't autocorrect and tried to spell the word with a capital M. Anyway, so this walkie-talkie had 500 megawatts of power, which meant that this walkie-talkie could probably power, and this is all off of a 2 AA cells, power like a dozen houses worth of power off of these 2 AA cells, and it was utterly ridiculous. And I wouldn't want to put that much RF power next to my head anyway. So anyway, you have to be careful that when you write an M, you're very clear that it's either a lowercase m or a capital M. All right, that's definite. And the other is a gig, and that's capital G, and that's times 10 to the 9th. So those are the ones that are commonly used in electronics. If we get into the digital world, you might talk about tera, which would be 10 to the 12th. But that's more in talking about storage. We would not have anything in electronics that's in the terabyte, terawatts or tera amps or teravolts range. So these are the ones that are most commonly used. And again, no way around it. You just have to, let me get rid of this, or somebody actually believes that. You just have to memorize them. So any questions on what I meant by the base units? So these are your base units, and these are your prefixes. Yeah, we good, or questions?
I'm good.
Okay. So the next topic was conversion between prefixes. All right, so let's say, for example, we wanted to do a problem that was convert 2.7 megohms to k ohms. All right, we said that the process we were going to use was the first step, we get rid of the prefixes and write the powers of 10. So we have 2.7 megas times 10 to the 6th ohms. Okay, so what we've done is we've gotten rid of this and we've replaced it with that. And we want to convert that to some number of k ohms. Well, k ohms is times 10 to the third. K is times 10 to the third. So again, what we've done is we've gotten rid of this and replaced it with this. Then we said the rule we use if we're going to a larger prefix, move the decimal point left. And the easy way to remember it is larger starts with an L, left starts with an L. You have to remember we're going to. So in this particular case, we're going from 10 to the 6th to 10 to the 3. 10 to the 3 is a smaller prefix than 10 to the 6th. So we're not going to move left, we're going to move right. So 10 to the 6th is smaller. 10 to the 3. Wrote that wrong thing. The one we're going to, 10 to the 3, is smaller than 10 to the 6th. So move not left, but right. So I write my 2.7. And I know I'm going to move right. And the space that we move, the number of places we move, is the difference between these two. So 6 minus 3 is 3. So move 3 places right. So we're going to move 1, 2, put in a 0, 3, put in a 0. So we would now, the next step would be to put the prefixes back in. So my 2.7 mega ohms is going to be 2,700 k ohms. All right. Questions? We good?
Yep.
Hopefully you're sitting there in the back of your minds going, my God, he's boring me to death because I already know this. But if you don't, let's go over it anyway. So let's do one more. So convert 300 microamps to milliamps. First step, get rid of the prefixes. So 300 micro is times 10 to the minus 6. And we want to convert that to milli, which is times 10 to the minus 3. All right. We're going to 10 to the negative third, which is greater than 10 to the negative 6. So we're going to a larger power of 10. So we're going to move left. And the difference from negative 6 to negative 3 is 3 places. So we're going to move 3 places to the left. So I would write this as 300. The decimal point is here. I'm going to move 1, 2, 3 places here. So that means when I put the prefixes back in, 300 microamps is equal to 0.300 milliamps. Okay. Questions? Or are we good? Yes, no? Okay, hearing nothing, I'll assume that that means we're all good. The next part was Ohm's law.
Come on, open, bro.
Okay, so Ohm's law. The big thing with Ohm's law is going to be a matter of making sure that you use the same current that associates with the resistor, the same voltage that associates with the resistor, which is not necessarily the supply voltage. So for example, if I did this, if I had a circuit like this, and let's say for argument's sake, I had a milliammeter in here, and that's going to this resistor. And then I had another resistor over here. And let's say for argument's sake, let's call this R1 220 ohms. Let's call this R2, oops, 680 ohms. And I'll give you the rest of it in a minute. I need to, and let's say this is R3, 1.1 K ohms. And let's, for argument's sake, say this is 10 volts. And let's say for argument's sake, we have a voltmeter over here. Oh, let's not make this 1K. Let's say we had a voltmeter over here. Calculator quick. Let's say we had a voltmeter over here. Let's say we had an ammeter over here. And let's say we had a voltmeter over here. And let's say this milliammeter read 1 milliamp. This voltmeter read 0.68 volts. This milliammeter read 1 milliamp. and this one read 9.1 volts. And this, of course, is 10 volts. So now, if I said to you, calculate V sub R1 I sub R2 and R3, what we would do is we have to remember here we're looking for V. So V sub R1, we know that V is equal to I times R. But we want to make sure that we use the current that's flowing through R1 and the value of R1. So the current that flows through R1, this milliammeter is measuring that. Current has to go through the milliammeter, out of the milliammeter into R1. That's going to be 1 milliamp. And we're going to multiply that times 220 ohms. So that should come out to be 0.220 volts. If I wanted to find I sub R2, we know that Ohm's law says I is equal to V over R, but we have to make sure that we use the voltage across R2 and the value of R2. So the biggest mistake that people make is they take and always use 10 volts, and that's not the case. The voltage that's associated with R2 is the 0.68 volts we see over here. So that would mean we'd have the 0.68 volts divided by the value of R2, 680 ohms, and that should come out to be 1 milliamp. And if I wanted to calculate the value of R3, we know that Ohm's law says R is equal to V over I, but we want to use the V that's associated with R3, which is the 9.1, and we want to use the I that's associated with R3. The current over here, we're told, is 1 milliamp. And when you work all of that out, that works out to be 9.1 k ohms. So the whole idea here is the different forms of Ohm's law. V is equal to I times R, I equals V over R equals V over I. Whoops, I forgot to put the V sub R3 and the R sub R3 over here. But the thing is that we have to remember that when we plug into these formulas, we always use the voltage that's associated with the resistance and the current that's associated with the resistance, not the supply current. Okay, the only, whoops, whoa, yeah, that's right. The only time you would use the supply current is if you're using, and this is a series circuit, which is not on the exam, if you wanted to check. This happens to be a series circuit, but we don't need to know anything about series circuits to solve this. All we need to know is that this meter is measuring the current that goes through here. This voltmeter is measuring the voltage that's across this resistor. This current is milliammeter is measuring the current that goes into this resistor. This voltmeter is measuring the voltage across that resistor. And we can just say the voltage associated with R3 is this, current is this, voltage associated with R2 is this, current associated with R1 is that. Okay? Questions up to here?
Nope, sounds good.
Hey, Professor,
Yeah.
for the first one, could you write it as 220 millivolts? I know.
Oh, absolutely. Sure. You could write this as 220 millivolts because they're equal. Yep.
Okay.
Let me pull this down a little bit. The last topic on the exam is going to be power. And we remember there are three power formulas: P equals I times V, P equals I squared R, P equals V squared over R. So if I was going to solve for P sub R1, I have my three choices. Which of the three formulas would I use? A, B, or C? If in this circuit I was looking for P sub R1.
B,
Why? I agree, but why?
because like the only thing that's given to you in that is the resistance and the current.
Right. We always want to, where possible, use the given values. So in this case, I was given this is 1 milliamp and I was given the resistance. I calculated the voltage, but what happens if I made a mistake over here? If I made a mistake over here, that's going to guarantee that this answer is going to be wrong if I use the voltage. By using the given values, we reduce that possibility. Just like with any of the Ohm's law, we always have to make sure that if I'm looking for P sub R1, then it's going to be I sub R1 squared times R1. All right? Current associated with R1, the resistance of R1 is going to give you the power for R1. So I have 1 milliamp squared times 220. $220 microwatts. Okay. P sub R2, if I wanted to do that, I would use the voltage and the resistance because those are the two given values. So V sub R2 squared divided by, let me draw that a little bit better. Divided by R2. So I've got 0.68 volts squared divided by R2, which is 680. $680 microwatts. And if I was solving for P sub R3, then I'd use the I and the V that were given. So this would be I times V. So this is I sub R3 times V sub R3. So I've got 1 milliamp times 9.1 volts, which gives me 9.1 milliwatts. Okay, so again, there's three different forms of it. Just like the Ohm's law formulas, you're just going to have to memorize them. With Ohm's law, if you're really desperate, if you remember the little, if I'm looking for I cover up the I, it's V over R. If I'm looking for V, cover up the V, it's I times R. If I'm looking for the R, cover up the R, it's V over I. So you can always use this as a memory device for Ohm's law. Power, there's 3 different forms. There's no little handy dandy little pie shaped thing that we've got. You just more or less have to memorize them. But once you've got them memorized, it's important to remember you're always using, if I'm looking for R1, it's the current, the quantities associated with R1, R2, the quantities associated with R2, and so on. There'll be some generic questions. Let me talk for a couple of minutes about the exam itself. Part 1 is multiple choice. Conceptual stuff. Okay. More or less, do you understand what's going on? Also, did you read the textbook? Because some of the questions might be out of the textbook that we didn't necessarily mention in class. So if you didn't read the chapter, I would go back and read those, at least read the summaries at the back of the chapter if you haven't got time between now and then. I started doing that. I used to give all calculation problems. And one summer I was teaching a physics course, and I happened to actually have 3 of the ELT guys in my class. And we were doing an experiment, and I had one group that was getting A's on their exams and probably had a 90 average between the 3 of them. And I had my 3 ELT guys who probably had about a 68 average, if that's generous, between the 3 of them. We were doing a lab, and the lab didn't work. So I said to the one group, that they came up to me and they said it didn't work. So I said to them, well, tell me what's going, what should be happening. And they just sort of sat there. And one starts to pick up a calculator. I said, no calculations. Just tell me what should happen here. They couldn't do it. They were absolutely flabbergasted, could not do it. So I got their problem up and running. About 10 minutes later, my 3 ELT guys called me over and said, it's not working. And I said, well, tell me what it should be doing. And they proceeded to explain exactly what should be happening and why what was happening was wrong. And I said to myself, what's wrong with this picture? The 3 ELT guys who understand exactly what's going on but screw up the math calculations are barely passing the course. The 3 people who are bound to get an A in the course have no clue what's going on but can crank numbers. So I always on my exams do a conceptual part, which says, show me that you know what you're doing, even if you can't do the math really well. And then part 2 is the calculations. So, you know, if I go back to here a minute, this stuff would all be part 1 questions. You know, what are the units of resistance? What are the units of voltage? What's the designator for current? What's the designator for power? Pico means 10 to the minus what, or 10 to the what. Okay, so that's conceptual kind of stuff. This, the conversions, and this, the calculations, are your part 2 stuff. And when you do the calculations, show all work. Because if you do something like this, I look at that and go, this is wrong. Now what I do is I go back and go, okay, use the right formula. That's good. Plug the right numbers into the calculator. That's right. This is a calculator error. So based on this, I would give that person pretty much full credit. I take off some points because it's an error in the calculator, but I would probably give them close to full credit because they had the right formula, they put the right numbers in, just somehow screwed up the calculation. That's a lot different than if all I see on the paper is this. I look at that and go, that's wrong, and I have no idea if that's wrong because they had no clue what they were doing, or it's a calculator error, or whatever. So this is going to be like 0 points, and this is going to be almost full credit. So I mentioned it before, always show me the formula, the numbers that are substituted into the formula, and the result that you come up with. So if you make a mistake, I can go back and figure out where you made your mistake, and if I can, give you partial credit. Okay? Okay, questions?
I just had a quick question on
Mhm.
the power portion of
Sure.
the exam. So
Yep.
can you actually go back to, yeah, there we go. P sub R2, when
Mhm.
you get that problem there. Hold on, let me just
Right.
type it in. 0.6 squared. Blah, 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 6. Okay, I get some weird, wacky number, 6.8 e to the negative 4. How did you know, like, how to simplify it to 680?
Oh, okay, sure. That goes back to what we talked about before, except without prefixes. So if I look at this, I could say this is going to be, all right, so you had 6.80 times 10 to the minus 4, right?
Mhm.
So what you want to do is, this is minus 4. We always want multiples of 3, right?
Mhm.
So I could either change this to times 10 to the minus 3rd or times 10 to the minus 6th. All right. So what I could do is, let's say I want to go to 10 to the 3rd, and that would be perfectly acceptable. I go 6.80 times 10 to the minus 4 equals what times 10 to the minus
Oh.
3, right? So I'm going to a smaller prefix. Larger would be left, so smaller would be larger prefix, excuse me. I'm going
Right.
to a larger prefix. 10 to the 3 is larger, negative 3 is larger than 10 to the minus 4. So I'm going to move it left. So I've got my 6.80. I'm going to move 1 decimal point. So I would be 0.680 milliwatts.
Mhm.
Or I could do my 6.80 times 10 to the minus 4 equals watt times 10 to the minus 6.
Uh,
All right. So now I'm going to have my 6.80. I'm going to go to a smaller, 10 to the minus 6 is smaller than 10 to the minus 4.
Right.
You know, you can think about your number line if you're not sure. You know, you got 0 over here.
Mhm.
You got 1, 2, 3, and so on. You got minus 1, minus 2, minus 3. Larger is moving that way. Smaller is moving that way. So minus 6 is smaller than minus 4. So we're going to move to the right. 4 to 6 is 2 places. So we're going to move 1, 2, 680 microwatts. So it's the
Gotcha.
same thing we did with changing prefixes, except there's no prefix. Which calculator are you using?
I'm using the TI-84.
Okay, so if you go, let me see if I can bring that up. Hold on one second. Yeah. It's coming up. Okay, you should be seeing the TI calculator now. Yes?
Yep.
Okay. So if you go to click on mode
Okay.
and up here,
Mm-hmm.
go down to this one and click on where it says engineering. Mine's already in engineering.
Okay.
So that's highlighted.
Mhm.
And then click second function quit. Takes you out of mode. Now, anything you do should give you answers in engineering notation.
Ah, okay.
So you don't have to go through that step we just talked about. It'll automatically come out in milli, mega, kilo, whatever.
Wow.
The powers of 10 that we talked about.
All right, cool. Thank you.
That makes life easier.
Thanks so much. Much easier.
And then we don't have to worry about converting. We're back to the whiteboard, right?
Yeah.
Okay. All right, other questions? Let me just say this. If in the event your calculator is out of engineering mode, I mean, you can always go back to this, you know, like we did as if it was a prefix conversion. That'll always work. Okay, other questions?
Sounds good.
If you understand what we went over, then I think we're in good shape. Like I said, there'll still be, in the conceptual part, there'll be some questions that are out of the textbook. So if you haven't really looked at the book, you might want to go back and look at that. And other than that, I think we're good.
All right.
All right. All right, see you tomorrow. Remember, the exam is not during our section, but it's going to be in the lab section. I'm not sure when Professor Atwood's going to give you the exam, whether it's going to be at the beginning or the end or whatever, but he's doing the exam. He's going to proctor the exam, and we'll just do a class in the morning. In the class at 1 o'clock, rather, not in the morning. Class at 1 o'clock. All right, see you then.
All right, thank you, Professor.
All right, take care.
Professor?
Yeah.
Like what pages should we read in the book?
What page in the book?
And like what chapters? Yeah.
Hold on. So the units and quantities is chapter 1. Voltage, current, resistance is chapter 2. Ohm's law is chapter 3. Energy and power is chapter 4. So it's on the first 4 chapters.
Okay.
All right?
Yeah, thank you.
Okay. Any other questions?
Nope.
All right. See you
Have a
tomorrow.
good one.